We'll start this video by returning to something that we mentioned a little bit earlier. Let's say that f and f prime are free modules with basis given by these vectors ei taken through an index set capital I and ej prime taken through capital J, respectively. So these ei vectors generate f, or are a basis for f, and these ej prime vectors are a basis for f prime. Then the tensor product, f tensor f prime, is also a free R module, and the basis, and it has a basis given by the collection of all of the elementary tensors ei tensor ej prime. So what are we seeing? We're seeing that the tensor product of free R modules is also a free R module. And if you have a basis for the first module and a basis for the second module, you can use those bases to come up with a basis for the tensor product. It's the most reasonable basis that you would guess. All right, so first, if f or f prime is 0, then this statement is clear. So let's suppose that they're non-zero, so both of these sets are non-empty. By this theorem 3.3 that we proved earlier, the collection of elementary tensors ei tensor ej prime form a spanning set for the tensor product. So what do we need to do in order to go from having this spanning set to having a basis? Is we need to show that this spanning set is linearly independent. So we need to show that if we have a relation among the elements of this spanning set, that is a sum overall I and j of Cij times ei tensor ej prime equals 0, where the Cij's are ring elements, where all but finitely many of them are 0, what we need to do is show that this relation is the trivial relation where all of the Cij's are equal to 0. What are we going to do? We're going to pick one element in this set capital I and one element in this set capital J and show that the coefficient, the ring element Ci0, J0 is 0. So we're going to show that one of these coefficients, one of these ring elements is 0, but the argument isn't going to use anything about which particular I0, J0 we pick, so it's going to apply to all of these together. So we're going to show that this relation is 0 by showing that every ring element is 0. We zoom in on a particular Ci0, J0. All right, so now we're going to use the fact that we know that f is a free module, free R module, and we have a basis for f to say, let's say v is any element of f, then we can write it as a finite R linear combination of our basis vectors. V equals a sum over I of vi times ei, where these vi's are ring elements, and all but finitely many of them are 0. Similarly, if w is an element of f prime, that's also a free R module, and we have a basis for it. We can write w as a finite R linear combination of our basis vectors. So w is a sum over j of wj times ej prime, where wj is a ring element, and all but finitely many of these are 0. All right, so now we've taken our element in our free module, written it as a finite R linear combination of basis vectors. We can zoom in at what happens for the particular element I0 in our index set I. Vi0 times ei0, same thing over in f prime. What happens at the particular basis element corresponding to J0? We have wj0 times ej0 prime. So I'll pause and erase, and we'll finish proving that this spanning set is actually linearly independent, so forms a basis for this free R module. Let's finish the proof of this argument continuing from where we were. We have this relation, sum over I and j of Cij EI tensor EJ prime equals 0. And we want to show it's the trivial relation by showing that all of thoseCij's are 0. And we want to zoom in on this particular one, Ci0J0. OK, we can express our elements of our free module in terms of the basis for each one. What are we going to do with this? The idea is to consider the appropriate bilinear function. We have a bilinear function, b, from f cross f prime to r, defined by taking b of v comma w and sending it to vi0 times wj0, the product of the two ring elements that occur in these expansions in terms of the bases that we're given. All right, this is a bilinear function. There are things to check. You really should check that you believe this. Once you have done this check, then by the universal mapping property of the tensor product, this bilinear function on the direct product corresponds to a linear function out of the tensor product. So there's a unique linear map, f0, from f tensor f prime to r, such that f0 of v tensor w is vi0 wj0 for each elementary tensor. Here's the picture of the commutative diagram that you get. F cross f prime up to the tensor product. This linear map f0 takes us down to r. And what you get is the same as if you apply b to f tensor f prime. Sorry, f cross f prime. So in particular, what does that mean? If you take f0 of ei0 tensor ej0 prime, you get 1. Why? Because if you take b applied to ei0 comma ej0 prime, you get 1. And if you apply f0 to a different one of these elementary tensors, ei tensor ej prime, where ij is not equal to i0 j0, then you get 0. So we have this relation, and we can apply f0 to both sides of this relation. On the right-hand side, we clearly get 0. And on the left-hand side, what do we get? We get c i0 j0. So what does that tell us? That says that c i0 j0 is 0. We do the same argument for any pair of something in I, something in j, and we see that every one of the ring elements in this relation is 0, which means that this spanning set is linearly independent, so it's a basis. All right, so again, what's the big idea? You're given a basis for f and a basis for f prime, and you can write any elements in your free module as a finite or linear combination of those basis elements. But then the big idea really is to construct the appropriate bilinear function, which is going to give you the appropriate corresponding linear function from the tensor product to somewhere. So the important thing to remember in how this argument goes is that this is the function that you want to consider. All right, so I'll pause and erase, and I'll talk about one particular example involving this result, and then we'll prove one more thing that we talked about a little bit earlier. We'll find a tensor that is provably not an elementary tensor. Let's discuss an example building on this tensor product of free modules is free result that we just proved. Let's say that K is a field and V and W are finite dimensional vector spaces over K with bases E1 up through EM and F1 up through Fn respectively. Then, well, we have a basis for one free K module and a basis for another free K module. And the tensor product is free, and we can get a basis for it by combining the bases in this way. Then EI tensor Fj is a basis of size m times n for the tensor product V tensor W. What does that mean? Every element of V tensor W can be written uniquely as a sum over pairs I and j of Cij times EI tensor Fj, where these Cij's are elements of your field K. So I'll point out, as Conrad does, that a statement like this is true even if V and W are not finite dimensional vector spaces. If they're infinite dimensional vector spaces, We haven't talked about that at all yet, so I'll leave that for now. And I'll say that these statements are also in Dummett and Foote. You can compare corollary 19 in section 10.4 of Dummett and Foote and proposition 16 in section 11.2 of Dummett and Foote in the discussion of vector spaces that we'll talk about coming up soon. So I'll point out that some places that you go to read about tensor products will focus first only on the case of tensor products of vector spaces, where things are a little bit simpler to understand because you can do everything in terms of bases. So this is a good example to keep in mind. And you can come back and think about this more when we talk about vector spaces in chapter 11 of Dummett and Foote coming up soon. So I'll pause and erase, and then we'll finish off this video with one additional example. We'll find a tensor that we can prove is not an elementary tensor. The last thing we'll do in this video is discuss example 4.11 in Conrad's notes, an example of a tensor that is provably not an elementary tensor. Let's say F is a free R module of rank n, and it has basis E1 up through En. The tensor we'll consider is E1 tensor E1 plus E2 tensor E2. This is definitely a sum of two elementary tensors, but is it an elementary tensor itself? Well, what do elementary tensors look like? They have the form something in F, tensor something in F. What do something in F look like? Well, we have a basis, E1 up through En. So elements in F are sums of AI times EI, where I goes from 1 to n. These AIs are ring elements. These EIs are our basis vectors. So that's something in F. Same thing with different elements. In our second copy of F, we can think of a sum from j equals 1 to n of bj times ej. So every elementary tensor looks like a sum of AI, EI tensor, a sum of bj, ej. But by the bilinearity of the tensor product map from F cross F into F tensor F, or just by elementary properties of tensors, this is the same thing as a sum over all I and j from 1 to n of AI times bj times EI tensor ej. And we know from the result that we just proved that EI tensor ej forms a basis for F tensor F, for F tensor F. So what would it mean for E1 tensor E1 plus E2 tensor E2 to be an elementary tensor? That would mean that this was equal to a sum over I and j of AI times bj times EI tensor ej for some ring elements AI and bj. Well, let's just match up coefficients, right? This is a basis. So there's a unique way to write each of these tensors as R linear combinations of these basis vectors. So that means that A1 times B1 has to be 1. A1 times B2 has to be 0. A2 times B1 has to be 0. And A2 times B2 has to be 1. And now we're in trouble. It is not possible to satisfy all four of these equations in the ring R. Why not? Because A1, B1 is 1 and A2, B2 is 1. So that means that A1 and B2 are both invertible elements. So what does that mean? Invertible elements are not zero divisors. Therefore, A1, B2 equals 0 gives us a contradiction, because we know that A1 and B2 are not 0. They're not zero divisors. So how could you take the product of these two things and get 0? You can't. So the conclusion is that E1 tensor E1 plus E2 tensor E2 is not an elementary tensor. And you can do similar kinds of arguments to prove that many other elements in this tensor product, F tensor F, are not elementary tensors. So this is something that's a very common exam type of a question. This is an example that I definitely encourage you to go over carefully and make sure that you understand.